So we may consider this as a first example, the step response of a system in the closed loop configuration. The shape of the response is different, moving from a monotone, continuously increasing curve up to a fastly oscillating, but finally steady state approaching curve. So in any case, in spite of 2 orders of magnitude change in K, the system in this example remains Bibo stable. But it is not always so. The root locus technique will enable us to understand when and why a system in the closed loop configuration may turn from Bibo stable into Bibo unstable. The characteristic equation is 1 plus G open loop of S equal to 0. Here a slightly different symbol is used. Here GH is the symbol used to indicate the open loop, the overall open loop transfer function. Of course, the same equation can be rewritten as GH or G open loop of S equal to -1. Now you have to consider that S is the Laplace abscissa, and so generally it is a complex number. So you have to deal with this equation in the field of complex numbers. And I mean that generally for a given value of S, GH of S, or if you like G open loop of S, is a complex number. And so for this equation you have to apply equality criteria that hold for complex. So you have to establish that the module is the same, and as well as the angle is the same. So it is not enough to state this, because this is an equation written in the set of complex numbers. In order to have this equation valid in the set of complex number, you have to additionally or alternatively of the left-hand side, which is this one, the module of GH of S, equals the module of the right-hand side. The right-hand side is -1, so its module would be, by definition, positive and equal to 1. And similarly, in parallel to the magnitude criterion, you have to apply the angle criterion. And the angle criterion states that the angle of the complex number at the left-hand side equals the angle of the complex number at the right-hand side. What is the angle competing to any point on the negative real axis? It is P Greek. So this is the reason why P Greek appears here. But however, you have to consider that a point on the negative real axis can be reached not only by turning an angle of P Greek, but also making an integer number of circulations against around the origin. So the angle cannot be precisely located, because it can be located considering an even number of times the whole plane is run. All complex values of S which satisfy both the criteria at the same time are roots of the characteristic equation, and as a consequence, poles of the closed loop system. Now we make a first important hypothesis. We omit any other dynamic system that is not represented in a rational form. So we make the hypothesis that our dynamic system can be represented and is actually represented by a rational function only. So we are keeping the time delay, the dead time, outside of our analysis. And we are considering dynamic systems that are of a rational form only. So we may adopt a factorized polynomial pole and zero form of the open loop transfer function, which like this one. K, which is a constant, is the transfer constant, times S plus Z1 times S plus Z2 times S plus Zm. This means that we have m zeros of our closed loop transfer function. And the denominator is S plus P1 times S plus PQ times S plus Pn. It means that we have n poles of our transfer function. Please consider that this is the open loop transfer function. Then after such an hypothesis, we have to take this form and replace it here, because the characteristic equation is 1 plus. It is not GH equal to 0. It is 1 plus GH equal to 0. After that, we make a second hypothesis. So the second hypothesis is considering cases for which the number of zeros is lower or at maximum equal to the number of poles. This corresponds to the fact that for engineering systems, it never occurs that the number of zeros exceeds the number of poles. When we find a dynamic engineering system that can be represented in the Laplace domain by a rational transfer function, it will never have more zeros than poles. We may also have someone of the poles as well as also of the zeros, but it is more important for poles. We may have that one or more than the poles are actually zero. Now we take advantages of the properties of complex numbers. Magnitude criterion becomes this one, because the module of G open loop of S becomes the module of K times the product of the modules of all binomials at the numerator divided by the product of all the modules of all binomials at the denominator. This is a property of a complex number. Similarly, the angular criterion takes advantage of the properties of angles of complex numbers. So the angle of the complex number GH of S is the sum of the angles of all complex numbers appearing as binomials at the numerator, minus the sum of the angles of the complex numbers appearing as binomials at the denominator. Now, concerning the angle, I have to tell you something, because it is not easy to, or maybe tricky to determine the angle of a complex number. And so I like to alert you, to make an alert, and to show you some simple cases that are anyway significant. This is partly in Italian, but it's easy to understand. Let's consider a very simple complex number, P equal to A plus BI. Here I is the imaginary unit. A is a set equal to 3 and B is a set equal to 5. We can easily plot this complex number in the first sector, because you know A is the real part, so the abscissa is 3, and B is the imaginary part, so the ordinate is 5. What's the angle for such a complex number? In this case, it is very simply calculated as the inverse tangent of the imaginary part divided by the real part. Anyway, the situation changes when we are not in the first sector anymore. In fact, let us consider 4 different complex numbers, which are quite easy, and they are all located on B seconds of the sectors. +1 plus y, -1 plus y, -1 minus y, +1 minus I. They are located here in those dots. What's the angle for them? Or better, what's angle is the arctangent function giving us for such numbers? Well, the arctangent, as calculated as the ratio between the imaginary part and the real part, would give us angles which are +45, -45, +45, and -45. Now, 2 of them are wrong for sure. So, if we would like to use the arctangent command, you have to consider some corrections to the results, which are reported here. When you are in the first sector, the result is okay, is correct. In the second and in the third sector, you have to add 180 degrees to your arctangent result. But now we are more lucky because both scientific calculators, as well as the scientific softwares, here MathCAD has been used, provide some other functions which are different from arctangent and can give you the correct angle. In the case of MathCAD, which is used here, and you will not use it, the function is arg. In fact, arg is giving us the correct angles. Anyway, arg returns the principal argument of the complex number between -p Greek and +p Greek, including p Greek. So the angles for the third and the fourth complex numbers are calculated or are reported when counting the angle in the clockwise direction, and so as a negative numbers. So all values of the complex number S which satisfy at the same time the magnitude as well as the angle criteria are poles of the closed loop transfer function. So when we fix K, and of course we have zeros and poles, the two criteria allow us to calculate the poles of the closed loop transfer function, and to check if at least one of them is positive or has a positive real part. In that case, our closed loop system would be BIBO unstable. These criteria are used in a more extensive and in a larger way because they are used parametrically by changing K. So by allow K to increase from 0 up to infinite. For each new value of K, you will obtain a new set of closed loop poles and a new condition to check for BIBO stability. And it may happen that at a certain point, by increasing K, the BIBO stable closed loop system turns into a BIBO unstable. This will happen when the closed loop poles, will cross the imaginary axis. And so the root locus is the tracing or the mapping of the poles on the complex plane when k is increased from 0 to plus infinite. When k equals 0 means that the controller has been shut down. Feedback control loop does not exist anymore, and we have returned back to an open loop configuration. So the root locus consists in plotting the possible values of the closed loop poles when k is increased from 0 up to infinite, while keeping the criteria satisfied, magnitude as well as the angle criteria.